Greetings, the Astro 30 here, and today I'm going to assemble this Chinese purported 100 watt OCL amplifier, which has the quasi complementary output stage. Now OCL stands for output capacitorless. Basically that means there's no capacitor on the output, and well, the majority of amplifiers now are OCL, so it's not really any reason to call it OCL anymore, but that's what they call it, OCL. They had output capacitors on the early amplifiers to, well, limit the amount of DC offset at the speakers. That was really all their main job. Now, I've measured the hole centers between the TO3 devices and they're all over the place. So I've got this little diagram, and this is viewed from the top down, so that would be the component side, and it's like 29, 20 there, 29, 22 there, 29, 21 and a half there, and 29 there, which equals, between the outside holes, 279.5 or thereabouts. And the lacquer that they've put on this circuit board is rather sticky, because when I was measuring it, I had my thumb stuck there for a while. Then when I removed it, it was like flypaper. Oh shit, nearly fell off the chair. So I said in the previous video when I was doing the mal thing that I did actually have a solution for the mounting problem, and that is to use these 15mm M3 tapped nylon spacers, which means all I do is I put two on the ends of the screws. Now I'm not sure what size screw they're using, whether it's an M3 machine screw or an M4. If it's an M4, I have to change it to M3 because the thread is M3. And just put, well, the heatsink, the device, a screw, a washer, turn it over, a washer, a nut, and then finally the two standoffs either end, and that'll give me the ability to mount it into a chassis, and also help to isolate the transistors from the chassis. So that's my plan. Now I do have a schematic for this, and we'll go through that now. Okay, so this is the redrawn schematic. I do actually have the original one, which comes off of eBay, but it's only a very low resolution picture, and some of the values are hard to read when it's blown up. So what I did was, last night I went and redrew it and just made it a little bit more clearer laid out. So it's not that complicated of a design. So you got your 18 volt AC split rail coming in, going into a 4 diode full wave bridge rectifier made up of 1N4007s. Now this amp purports to deliver 100 watts, which is doubtful. You'd be lucky to get over 12. And using 1 amp diodes in a bridge rectifier for that amount of power, yeah, that just ain't gonna happen. And then it's put through some filter caps here, 1000 microfarad at 35 volt each, and there's two of them in parallel, and that makes it 2000 microfarad. And of course it's split rail because there's an earth point here, or a 0 volt rail. And so there's another pair here as well for the negative side. And this is one channel of the amplifier, this is the other channel, and it's made up of 7 transistors, 1, 2, 3, 4, 5, 6, 7. You've got your long tail pair or differential amplifier here, and they're just using standard MPNs. In their case they're using the Chinese S9014s, typical. So that's a differential stage. Then one output is going into VT3 over here, which is an S9012 PMP transistor, and this is known as a VAS, or voltage amplifier stage. They have here C3, which is a 100 picofarad capacitor. This is what's known as a millicapacitor. They put this across the collector and base junction of the VAS to help prevent the amplifier going into subsonic oscillation. in the megahertz range, which is not audible on your speakers, but will really heat the output stage up, and you'll end up with thermal runaway. An oscillating amplifier is not what you want. So to help combat that, they've used a millicap, which is pretty standard. It's usually 100 picofarad. And then we move on to the output stage. Now, if we look up here, the output symmetry of this is a quasi-complementary. But if you look at each side where the drivers connect to each transistor, the side of the amplifier that's positive going is this NPN Darlington stage. So this will be classed as an NPN transistor. So on the PNP side of the amplifier, we've got what's known as a C-clay-E compound pair. And it's named after its inventor. It's basically based on the Darlington, but it's not a Darlington, it's a C-clay-E. There is another word for that, but I can't think off the top of my head what it is. So this stage here would be classed as the PNP transistor. So the overall topology is still quasi-complementary, but we've got a Darlington stage and a C-clay-E stage. Now, biasing here is done via a resistor and a diode. In this case, a 1N4148. Now, yeah, this is fine, but it's not adjustable. And this value of resistor, if these two output devices are not perfectly matched, i.e. that they're not from the same batch, you're going to have a slight imbalance in tolerances. So you're going to end up with crossover distortion. You should really have some form of variable resistor here, or even a VBE multiplier to control the bias correctly, but that's beside the point. What I can do here is I can put a variable resistor in here instead of that resistor, and then adjust it so for the least crossover distortion, and then pick the relevant resistor after measuring the potentiometer. Now, R6 and R5 form the gain of the amplifier, and this topology of discrete amplifier is exactly the same as an op-amp. You've got a positive input, non-inverting, and an inverting input here, and an output obviously. So if we class these two resistors as going from the output to the inverting input of an op-amp, we can calculate this amplifier's gain, and I'll just demonstrate that now. So let's look at how we calculate the gain of a non-inverting op-amp. We have R1 here, R2 here. This is the feedback resistor going to the negative terminal, or the inverting input of the op-amp. Got your normal signal input here. And the way we calculate gain is gain equals 1 plus R2 divided by R1. So R2 divided by R1. So say for example that R2 is 22K, okay, and R1 is 1K. So if you divide 22 by 1, it comes out as 22. Plus 1 to that, then the gain equals 23. So with this configuration, we have a gain on this op-amp of 23. Okay, now based on that demonstration, assuming this was R2 and this was R1, we could then go 1 plus R2 divided by R1, so in this case 33K by 240 ohm. Now the problem is that's in ohms, that's in K, so I'd have to convert that into ohms, which would be, well, times 1,000, would be 33,000 ohm divided by 240 ohm. So that comes out to a gain of 137 plus 1, so 138. That, for this, is an extremely high amount of gain. So in actual fact, that's way too much gain for this circuit. It's okay if you're not planning on using a preamplifier ahead of this, which is what you're supposed to do. I think their intention was this can be connected up with a volume pot at the front, and you can connect it up straight to a CD player and not have to worry about a preamp. However, I want to put a preamp on this so I can control bass and treble and things like that. So this gain will have to change. A more satisfactory gain would probably be a gain of 24, which is a 22k resistor and a 1k resistor there, because the input sensitivity of this would probably be 300 millivolts for full output, and any good preamplifier will put out 2 volt peak to peak before clipping, so you really need an input sensitivity on this of 1.5 volt peak to peak. So, but we'll do testing on that, and I'll leave the original values in here and then change them later. So let's first get the thing built, and then we'll worry about what its output power is and what its gain is, because I want to find out how much current one of these amplifiers draws. There's a reason for that, because there's, well, a couple of problems with this design. There is no fuse protection anywhere in the circuit, so there is no output short circuit protection. There's no VI limiter or anything else like that, so that if one of these output devices gets shorted to ground or earth, well, it'll take out the output stage. The output stage will not last very long. Transistors do not like being shorted. So if there was an inline fuse in here somewhere, well, it would just blow the fuse and hopefully protect the output devices. So there's a way of solving that without having to cut a trace and put in a fuse holder onto the back of the chassis or something, is that in each output we put what's known as a poly switch, or PTC. Now what these are designed for, they're designed to work like a fuse. They have a trip current limit, somewhere in the order of 1.5 amps to 3 amps depending on the PTC you use. And as soon as you get a short circuit to earth, well, you're going to get quite a fair amount of current draw going through the circuit. So as soon as it reaches that threshold, its resistance, internal resistance of the poly switch, increases, therefore no longer appearing as a short circuit across whatever it's connected to. And in normal conditions it has a very low resistance. I don't know what that is, it's below 0.1 of an ohm anyway. And under normal conditions it'll allow the signal to pass out quite naturally to the speakers until the speaker terminals are shorted to earth altogether. Then it will act like a fuse, increase its resistance and remove the short, protecting the output devices. It's exactly the same as they used to do back in the 70s and put a fuse in line with the output. But a lot of audiophiles say that it adds to the distortion, but there is no audible test for that. You can't hear it. It's just a bunch of crap. The other problem with this amplifier is there's no Zobel network, which helps prevent the amplifier going into the onset of oscillation when you've got long cable runs to your speaker. I'll just show you what a Zobel network is, and then we'll get into actually constructing the kit. Now, some of you may not like all this in-depth theory or sub-theory, but I think it's important that when you're building something, or you're building something that you've never built before, that you actually learn a little bit about what it is that you're building, like how it's supposed to work, so that when it doesn't, well, you know where to go. Now, back to the Zobel network. You have your amplifier here. You've got inputs and you've got your negative feedback, etc. So that's the input, and that's obviously the output. Now on the output, normally what you should have is a resistor, usually 10R, and a capacitor going to earth, which is usually 100 nanofarad, and this will prevent the amplifier going into high frequency oscillation. So this is what's known as a basic Zobel network. That's fine, but sometimes this alone is not enough. So what amplifier designers often do is they put another resistor, usually 10R, it can be anything, and an inductor. on the output, and then that goes off to your speaker. So this is actually a full Zobel network. The value of this inductor, well, for this demonstration, isn't important, and that's actually selected on test. You have to actually hook up an oscilloscope, put on a long speaker lead, and actually get the thing to oscillate first, and then work out the number of turns you need to add to this inductor to stop or prevent the amplifier from doing that. And the oscillation on the amplifier that the speaker leads can cause can be in the megahertz, so keep that in mind. So we call this select on test. So you'd actually have to put it through a measurement test into a dummy load on a long speaker lead run, usually up to 100 meters long, just to get the amplifier to oscillate. And a lot of amplifier designers spend a lot of time trying to get it to oscillate. So that's the Zobel network. It prevents the amplifier from going into subsonic oscillation due to the length of the speaker leads. The longer the speaker leads, the more likely the amplifier will go into subsonic oscillation. And getting back to the poly switch, basically a poly switch is a resistor like that, and then that goes to your speaker. So if this was suddenly taken to ground, this, which has a very low impedance to start with, will become a very high impedance. As I say, the resistance will go up, therefore loading the amplifier down with a higher resistance or higher impedance, which is no longer, from the amplifier's point of view, a short circuit. So my plan is I'm going to build this circuit into a case, but I'm going to add in one, a Zobel network as described here, and two, a poly switch. But because all poly switches are not equal and they have a different trip current and different amount of handling in watts, like how much wattage can go through it before it trips, I need to know what the output power of the amplifier is and what current it is drawing so I can select the correct PTC to stick on the output. Anyway, that's enough theory. Let's get on with assembling the kit. God knows what the hell they are. Some Chinese knockoff of something, but yeah, they're not the best looking transistor in the world. The actual 2N3055s have a thicker base plate than that, or I should say collector. Yeah, it's just, yeah. So what I'm going to do is I'm going to assemble all the small components first, like resistors and diodes, and then move on to the capacitors, and there's an LED here you've got to put in. I suppose that's just a power indicator. Then I'll move on to the larger 1000 microfarad capacitors and the connectors. And when I've actually got up to that stage, I'll come back before mounting the output transistor. So in the next shot you will see this almost completely built. Also, I've put some rubber feet on the bottom of this solder stand to stop it sliding around the desk. And also my helping hand that I normally mount circuit boards into, this board is going to be way too big for that, so I'm going to have to go back the old way and assemble it on the desk. And this was also in the bag of components, which I can't read Chinese, but it is a date, so it says 2018, the first month, so this was packed in January, just for your knowledge. I think that's just like a quality control card, like a person signs off that they've included all the components correctly. Well, interestingly, before I've even started, I've run into my first problem. There's this rogue 20k resistor in here, which there is no place. Oh, I'm sorry, yes there is. R23 is a 20k on this board, but according to the schematic it's a 10k. So they've changed it to 20. Alright, fair enough. Now one thing worth mentioning here is there's two little jumper connectors, J1 and J2, which link, I believe, the earth together for the amplifiers, if you don't include these jumpers, it's not going to work. So it's worth noting that those are there and you need to put them in. So just in case you don't initially see them, but I'm just pointing out now that there are two there. I believe it's just connecting the 0-volt rail together for both amplifiers, so it's grounded. Actually, I just checked that. It goes across the negative of these two sets of capacitors here, so it's actually connecting the negative rail of both amplifiers to the negative. Don't connect that and it definitely won't work. Okay, got all the resistors installed. Was fairly painless. I just measured them with a multimeter to double check what their value was, and as usual I've put all the bands facing the same way around, so when I turn it that way, which is the correct way around to me, wrong way around for you, I'm reading from left to right along the line there. Same with these, I'm reading from left to right. So now I'm going to move on to the diodes, which there's 6 of them, and yeah, then maybe the transistors, the capacitors, and then finally the large filter caps. Of course, speaking of capacitors, there's going to be a slight problem here. The two ceramics they've included are marked 103, which is 10 nanofarad, not 100 picofarad. It should be 101. So I'm going to have to crack into my arsenal of components to get the 100 picofarad capacitors I need, because, well, okay, yeah, 10 nanofarad as a millicap would probably work, but there is no reason for them to change it. They haven't even marked on the board the change, so I'm going to stick to what the circuit diagram says. Okay, and a short time later I've got the 4 diodes for the bridge rectifier, the 1N4007s, which are underrated for what they're trying to do here. The two 1N4148s and the two 100 picofarad 101s, ceramic caps for the millicaps, and the LED. Now I can move on to the 10 signal transistors, keeping in mind that there are two types, 9014s and 9012s. So be sure to read the case of the transistor first before soldering it in. Okay, that's all the transfer resistors done. Transistors. Actually, that's where the name transistor comes from. It comes from two words, transfer resistor. Just a little bit of a FYI for you. Now I'm going to move on to the capacitors. Now where P1 is, this connector here, which is your input for left and right, I'm going to use a 3-pin connector or header. But for testing, I have got one, but I don't want to muck around making up a cable just to test it, so I'll just have some fly leads coming in and out of it to do the testing with. The circuit board lacquer that they've used on this is very sticky, and you can start to see some of my fingerprints all over the board there. Don't know what type of lacquer that is that they've used, but it's almost like they've sprayed way too much on there and it hasn't cured properly. But anyway, moving on to the electrolytic capacitors, and that's almost the construction complete. Shenzing brand, cheap Chinese second-rate capacitors. If you were a real big audiophile here, well, one, you wouldn't be building this amplifier, and two, you'd use high-grade capacitors like Nichicons or something, not these Shenzing caps. Okay, and that's the module almost complete, apart from the output stage. As I said, I've got the power in and the output connector connected, all the capacitors in. There's only 8 of them. These 1000 microfarad 50 volt capacitors, even though the circuit diagram calls for 35 volt, doesn't matter. Or are they 35 volt? Yeah, the 35 volts, sorry. The rest are all 50. These, a smoothing capacitor, do not make very well. 2200 microfarad at the bare minimum is good for filtration of ripple. We've only got like 2000 microfarad here. It'll work, yeah, but these capacitors will after time dry out very quickly because, well, they're not actually rated to be used as DC filtering capacitors. So because they can't really handle the 60 Hertz ripple. Anyhow, that's beside the point. There's enough space here if I want to later change these to, like, I don't know, 2200 microfarad capacitors all across the board there, with low ESR and all that lovely jazz stuff, and just make it a little bit nicer. As it stands, there might be a little bit of hum and ripple on the output. We'll soon see when we put it on an oscilloscope. However, I'm going to move on to the last stage, which is mounting these heat sinks and transistors. And interestingly, they have given us M3 mounting screws for that. So that's nice. I don't have to change anything. I'll just screw my nylon standoff on the end of the thread here after it's screwed down. Now the thing is, with the transistor, the TO3, after you've straightened the leads, of course, is when you apply this to the heatsink, like so, make sure to smear some thermal grease in between the two to allow better heat transfer, or else these transistors will not last very long because the case will get hotter than the heatsink, so totally defeating the purpose of it. So it's pretty simple. It's just transistor heatsink transfer compound, heatsink, bolt through the top, nut on the bottom of the board, and yeah, solder it in. All this talking's made me thirsty. Keep it clean, guys. Okay, so just smear it around like that. Don't have to cover all the device. Once it actually screws down to the heatsink, it will spread out nice and evenly. Put this through the heatsink, like so, and then mount it through the board, like so. And then I'm going to take one screwdriver and one of the supplied nuts, and that magnetised straight to the transistor body. That was nice. Put him through the hole. Probably just hold the end of the screw, slip me nut on, and yeah, and before I tighten it all down, straighten these heat sinks and make sure that, because they can move around like that, that they're not actually making contact with the base and the emitter connections before soldering it and tightening it. So I'm just torquing them down finger tight so I can still move the heat sinks around, and I'm going to do a test between base and emitter and make sure that the heat sink is not actually shorting them out. That's conduction, so that's the base emitter junction. Conduction, so that's base emitter. Conduction, so that's base emitter. Conduction, so that's base emitter. If I reverse them around, nothing, 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 and nothing. So the heatsink is not shorting those out. So being an NPN transistor, that means the positive is the base, so I'll just check that there's conduction to the collector, which there is. There is there too. There is two there as well, and there as well. So I know that those transistors are working, they're not short-circuited or anything, so when I power it up, nothing bad should happen. So what I can do now is I can tighten these nuts down properly and then do a final check before soldering the transistors to the board. Alright boys, get your minds out the gutter. You'll notice that on a couple of these transistors here that some white stuff has come through where we need to solder, so we need to get rid of that thermal compound before we attempt to solder it, because otherwise it may prove a little bit challenging. So I'm going to spray some isopropyl alcohol on it Acetone would probably work better. And just get in there with a rag. A Q-tip would probably work a lot better than this, but yeah, that's all I've got to work with. I'm not sure what it is about electronics, but most things can be turned sexual rather quickly, or into at least a double entendre. Right, so just going to solder these leads in. I've verified that the transistors are still conducting as they should, and that yeah, see what I mean about that heat transfer compound? It makes soldering awfully difficult. That joint is pretty nasty, so I'm going to have to clean that one up a little bit better. But once I've soldered these in, we can move on to testing. Probably an advisable thing would have been to not have the compound around where the base and the middle leads are, because it just makes a mess on the other side of the board. Yeah, a toothbrush works better, I must admit. This is an old one, but it's not being used, so don't use the toothbrush that you used to brush your teeth with, because otherwise you may end up getting alcohol poisoning. But this is the best way to get all that crusty heatsink compound now that's been soldered into the joints away from the board, so we can touch the joints up and make sure that we have some decent joints there. Because once you've cleaned it up with isopropyl alcohol, you'll notice that the joints look very dull. So that will lead to a problem later down the track. I mean, for this sort of project, this kit, who cares, right? But yeah, at least make a decent effort of the job. Okay, I've taken some solder back off with the solder sucker and cleaning these joints a little bit better, trying to get as much of that compound out. That was my mistake. I haven't dealt with TO3 transistors in a long time, and usually I've never had this much trouble with them, but there's always a first time for everything, I suppose. So I'm just carefully soldering them now. I mean, I'm getting a much better joint now than I was before. It's a lot. That one's not taking very well. I think it has taken, but it looks very crystalline to me. So once I cut that one off, I'll investigate him a little bit further. While trying to solder a flywire to that, I nearly ripped the pad. Well, actually I did rip the pad slightly off of the circuit board. That's the input connector, so I'm going to have to be very careful with that. So what I'm going to do is I'm going to solder some stripped wires instead, and then I'll buy a 3-pin connector for that. I don't want to damage it if I can avoid it. Alright, so we have got a yellow wire which is connected to the capacitor, which is supposed to be the right input. So they've actually got this backwards on the board, like when you look at it like that. This is the left hand channel and that's the right hand channel, but yet that's the input for the right hand channel, so they've actually got them inversed. Doesn't really matter, but anyway, the right is the yellow, the orange is the left, and the white is the common or ground. So one other thing before we move on to testing is I was talking about these nylon standoffs. So I need 2 of those, and what I was going to do is just connect them or screw them onto the ends of the screws from the transistors, if it will thread on for me. And there we go. That solves the mounting to a chassis issue. Of course, there's going to be a bit of pressure on the front here, so you've got to keep that in mind, but that'll solve how you're going to mount it. And it's isolated. Okay, now we're ready for some testing. But first, I've been waiting on this in the mail for quite some time too. Now this is going to be very important to testing, and I'm hoping that this is what I was expecting it to be, or else I'm going to look like an idiot. But it does say description of contents resistor, and it's quite large. Any guesses as to what it is? Hey? Give you a few seconds whilst I open the bag. Any closer to guessing what it is? Let's get this styrofoam off and find out, eh? This, it's a bit frayed there, but this is what's known as a dummy load. This is measured at 8 ohms, and this can handle 200 watt, I believe it was. It cost me about $20 off eBay. That's where it came from. Sure Electronics. Yeah, so there you go. So this should be able to handle up to 200 watts, as I said. The aluminium is a bit poorly manufactured, but this is a heat sink. So there it is, 200 watt, 8 ohm. And this is what you need to use when you're measuring amplifier outputs. Is you do not want to connect an amplifier to a speaker and inject a signal and measure power output whilst it's going into the speaker. One, that is deafening. Two, it's not very healthy for the speakers. Because if there is a problem with the amplifier, you want to know before sacrificing expensive speakers whether or not there is a problem with the output, and that's the whole importance of a dummy load. Now, because this is a heatsink, you don't really want to place it on top of the desk like that, because you might end up burning a hole through it, depending on how much wattage you put through it. I doubt this module is going to cause that issue, but what I'm just going to do now is I'm going to measure the resistance of that resistor. Yeah, about 8.5 ohm, which is close enough. So this gets connected across your speaker output terminal, ground and active, and then you connect your oscilloscope probes across it. So let's get myself set up here. I'm going to move some stuff and move you onto the floor so we can get a better angle, clean up the desk a bit, and get on with some testing of this OCL piece of crap amplifier. Okay, so now what we're going to do is what's basically known as a power on smoke test. Now, I've got the positive lead of the power supply connected to the cathode of the bridge rectifier, and the anode of the bridge rectifier on this side connected to the negative, and one to the ground. So what I'm going to do is I'm going to start off at 0 volt. I'm going to turn the load on, and as we notice there is no current draw, and I'm going to slowly wind up the voltage. It's 18 volt, 18 volt AC, so when that's DC, that's 21.21 volts. So I'm going to slowly increase this voltage, watching the current, to 21 volt, and if this suddenly starts to go higher than a few MA, like into the realms of 1-2 amps, there is a problem. Stop going, shut it down, and check for problems. So right now nothing's happening with the heat sinks, so the load is on. I'm going to slowly wind the voltage up. Now we're at 0.8 of a volt, 1 volt. The LED down here is starting to turn on, but it might be out of frame. 2.9 volts, 5 volts, the current's not doing anything. We're now at 10 volt, current still not doing anything. I'm measuring at single rail, by the way. So because the current is not suddenly increasing, there's a little bit of a jump there. I know now that when I get it to 21, which is its full output voltage, about there, that there is no problem with this circuit. It's not oscillating either because the heat sinks are cold. Now what I'm going to do is I'm going to measure the DC offset on the outputs here. It shouldn't be any more than 100 millivolt per channel. So we'll go down to 200 millivolt. Hopefully you can see that meter. The earth is there. We have 60 millivolts, that's perfectly fine. That's on the right channel. Whoa, left channel just went off the scale. We have full DC voltage coming out of
the left channel. Okay, so I need to find out why. It shouldn't be 19 volt. So that was a very good thing to do first, is to actually test the output voltage before connecting anything up to the output, because that would have blown a speaker instantly. Okay, so I'm a little bit closer to finding out what the problem is. I dropped the voltage down to 9.2 on the supply. I've hooked it up across the bridge rectifier, so between negative and 0 I've got 8.5 volt supply. Now I'm measuring at the cathode and the negative of these biasing diodes, and on the left channel, the bad channel, I was getting like 12-13 volts coming off the cathode. Now I'm getting around about 8 volt there, and comparing it to the working channel, I've got 8 volt there. So I know that the biasing network is biasing the driver transistors properly, but as soon as the output transistors are connected, it all goes to hell from there. So I'm doing some testing here. I want to see, well, I know what's coming out of the VAS, which is Q3, which is collector, because that connects to R7, which is a 220 ohm resistor. This is actually backwards. This should be right, that should be left, but that's beside the point. I know which one's which on the board. It's just backwards on the schematic, or backwards on the board, right on the schematic. So at the 220R, which is actually R18 instead, and negative, I'm getting 9 volt. That should be with reference to the positive rail, which is sitting at 9.6. So there's actually an imbalance in the power supply, but yeah, that's really neither here nor there. So the VAS is giving me 9 volt on that channel. On the working channel, which is R7, I'm also getting 9 volt. So coming off the collector of the VAS is 9 volt. So at the base of the VAS, which is Q3, I think base is pin 1 on these transistors. I reckon that would be the emitter, because that's giving me 18 volt, which is the full voltage across both rails. So it should be that pin there. That's 8.9. That's going to 9, so that's the collector. That's the base, that must be the collector. No, that must be the collector. That must be the base. I'm going to have to look up the pin out of these stupid Chinese transistors. Okay, I've just verified the pin out. As you look at the front of the transistor, say this is a S9012, the 9014 is the same. Pin 1, which is on the left, is the emitter. Pin 2 is the base, so the center lead is the base. And pin 3 is the collector, which means that these transistors are comparable to the 2N3904 and the 2N3906 transistors. Therefore you should be able to substitute them if you've got a bad one with one of those either or types, because the emitter is on the left hand pin, just as the emitter is on the left hand pin of these. The BC54 and 55 range, the collector is on the left, so you'd actually have to reverse it in circuit, and it would still work. So now that I know what the pin out is, I want to find out on Q3, which is the VAS of the good stage, the base voltage going in with respect to either negative or positive. So I need to get into base pin. We've got we've got full line voltage because we're going through R3 4K7, so that's fine. So I want to know what Q10's base is doing. Exactly the same, 17 volt. So I know that the amplifier stages are actually working. Just one not with the output stage connected. So I'm going to put them up to the full 21 volt. And what's even more interesting, it was giving me the negative rail at the speaker output, and that was kind of interesting, but it was drawing no current, so it wasn't a direct short. So it turned out that the output stage was being biased hard on. Now, I don't appear to have any voltage now on the bias of that channel, and I have 18.5 volts on that one, but none on this. It's not biasing it anymore. That could be because the output stage is disconnected, but I should have with respect to there. Okay, so I got 40 volts there and only 21 volts there. So for some reason I'm getting 40 volts across that one instead of 21. So it's actually biasing the output stage hard on. Well, the drivers anyway, so that's not right. And I really need to think about checking these transistors. Now this is where having a dummy load is important, because when I connected that up to the suspect output channel, which is still giving me 19 volts there, I've resoldered the transistors back in because I cannot find any physical fault in the circuit. The output dropped down to 12 volts DC negative, and when I looked at the display here for the current, it was 1.5 amp. So I do believe the left channel is actually oscillating. Let's see if I'm right. Okay, so I've got my oscilloscope, DSO, whatever, set to 5 volts per division, and the time base of 1 second by the looks of things. Turn on the power. Well, I don't see anything on the scope output, but I have 1.52 volt. To 1.52 amp. I'm touching the left input of the amplifier and it's not even giving me a blurt on the screen. So I know that that's drawing way too much current, and oh yeah, that transistor there is red hot. So there's a fault in this circuit somewhere where I just cannot figure out what it is. So this thing is a waste of my time. I really do not want to continue on mucking around with this Chinese shit, because I've got better things to do and I don't want to sit here all afternoon fault finding it. So what I'm going to do is I'm going to move on to the known working channel. So all I've got to do is just swap one lead. Okay, lead swapped. Now I'm getting a lot of random noise. So that's the right channel there. See, that is working like an amplifier. And if I change that to, say, 2 volts per division, about 2 milliseconds. Yeah, so that channel is working as an amplifier. Maybe one day I'll fault find this, but I really can't be bothered. So I'm going to inject a audio signal into that, and we're going to have a look at what sort of output we're getting. Okay, got the function generator hooked up. We should actually start seeing an output once the thing... Well, I'm at 1 kilohertz, 1 volt output. Nothing on my scope, but I might be connected to the wrong input, although it doesn't look like I am. Oh, I know why it's not working, because it's turned off. That might be a good reason as to why. Make sure which one's which. Yeah, it's the yellow one. So we connect that up, and there we go, we've got an output signal. And I can actually hear that whistling. We're drawing around about 800 milliamp. So I'm going to change the volts per division, About 300 millivolt, clipping at 300, reasonable at 200 millivolt. Okay, so we've got 200 millivolt peak to peak there going in, and we've got a Vmax of 17 volt coming out with a current draw of around 500 mA, which is pretty small. We now need to work out what the power output is. There is several ways of working out what an amplifier's power output is in watts. The simplest is the power law, P equals E times I. So that's your voltage, peak to peak, times the current draw. So in this instance I've chosen 48 volts peak to peak and 1.5 current draw. That equals 72 watts. The more complicated way of doing it is if you don't know what the current draw is but you know what the load, the resistance is, you can use V peak, which is different to peak to peak. Peak to peak is, you've got your zero line and there's your AC waveform. Peak to peak is from here to here, so that's from there to there. V peak on the other hand is from the zero line to the peak, or it could be to the negative peak, but it doesn't really matter. If it's a sinusoidal waveform and they're equal on both sides of the zero line, you can use either. So in other words, it's half the peak to peak voltage. So that gives us a voltage of 24 volts. So the V peak, I'll just write V peak is 24 volt. That just keeps the math a little bit more simple. Now, the way you work out the power is you take the V peak, 24 volt, times it by itself. So that's V peak 24 to the power of 2. So 24 times 24, which equals 576, divided by your resistance, which is 8 ohms, equals 72 watts. So you can use this to work out what either one actually, you could use either one of these to work out what your wattage is. This is if you know the current, this is if you know the resistance. Well, you should know the resistance but don't know the current. You can always measure the current, but either of these will work. But you've got to remember, in this peak one, you've got to use V peak, or half peak to peak. You cannot use peak to peak. It has to be half of it. Now down the bottom here we've got something known as RMS, which is, well, in the electronics industry, to a lot of people, is a mythical value of measuring. However, to calculate that, you take your V peak again, which is 24 volt, divide it by 1.414. Now that is an interesting number. That's the same number we use to calculate AC to DC voltage through a bridge rectifier. Isn't that funny? It's the same figure. Anyway, it's V peak divided by 1.414, or to make it even simpler, just 1.4 to the power of 2. So that's this result times this result. So it's multiplying that against itself. So, and then dividing it by the resistance, as we did in the peak example. So V peak divided by 1.414 is 16.973, which to the power of 2, or 16.973 times itself, is 288.08, divided by the resistance, which is 8, gives us 36 watts RMS. Realistically, RMS you shouldn't really ever have to use. What is more important is the peak voltages. So because I already know what the current draw is and I know what the peak to peak voltage is, I can just use the simple equation here to calculate the current output wattage of that amplifier module. Okay, and because I'm lazy, I'm going to use a calculator. So it's P equals V times I. So we've got 17 volt times the value of 500 millivolts in full amps, which is 0.5. 17 times 0.5 is 8.5. So the peak output wattage of that amplifier module is only 8.5 watts. Nowhere near the mythical 100 watt. Now, those transistors are red hot, so I think I'm going to kill that now because that's been running for quite a bit of while. And even running at close to 8 watts is, yeah, a lot of heat. And it's cooking. Yeah, and that's at where you have 18 volt coming in and rectified to roughly 21. So if it was actually at 21 on the supply, you'd probably have a higher output voltage, not by much, probably half a watt. So we'll say that the peak output power of this is only 9 watt, and that channel's not working for some reason. It's just outputting the negative DC rail onto the output. So I have no idea why, and quite frankly I don't particularly care, because I am in no mood to fault find. I'm probably going to have to end up just replacing transistors, because that's the only thing I can think of is there is an issue with transistors. It could be the output stage, could be, but for what I paid for the cost of that kit, which was like $10, why would I even bother? It was, oh excuse me, it was great for demonstration purposes of what problems can occur in an amplifier, and in this case we've got a DC offset of negative 19 volt coming out the output, and it was also a good learning tool for calculating wattage. Oh, I can't stop farting. Now it's 8.5 watt peak, but what is it RMS, in case anyone was wondering? Okay, so we've got 17 volt peak to peak, so we divide that by 2, that gives us our V peak, which is 8.5 volt. So we times that by, we divide that by 1.414, gives us 6.011, we'll say. So we'll say now 6.011 multiplied by 6.011, which is the power of 2, that gives us 36.132 divided by 8. We get about 4.5 watt RMS. Okay, so I'm putting about 50 millivolt into the input now. The input is very noisy. If I disconnect that's the speaker lead. Maybe if I disconnect the correct thing might help. If I disconnect the input, yeah, it's amplifying the signal, it's just noisy. Anyway, so that's this output capacitorless amplifier, as they call it, and even that's still maintaining quite a bit of heat. At least we know that the right channel works, but the left channel's garbage. As I say, I'm not going to bother fault finding it. I just bought it for an experiment, basically, just to, you know, demonstrate power output calculation and actually busting the myths of what they actually say its actual output wattage is, which is nowhere near correct. But as I said, having a dummy load when doing these tests is very, very important. So now it's drawing about 30 mA. That's pretty good. So I'm going to put this to bed now. This video's been long enough, so it's time to end the video, and yeah, thanks for watching. I'm the Astro 30, and if you enjoyed this video, please remember to rate, comment and subscribe below, and you can always follow me on Facebook and Twitter. The links are in the description as usual. Also, you can support me on PayPal by donating as little or as much as you want, because your donation allows me to buy stuff to play around with on the channel. And speaking of channels, check out this guy, 12 Volt Vids. He has some great content to do with electronics on his channel. Anyway, this is the Astro 30 saying see ya, have a great day.